Hello, welcome back, AP Physics kiddos. So today we're going to be talking about electric fields a little bit more and getting a little more quantitative. So remember how we map out an electric field is we put a test charge in the field. We look at the force acting on it, okay? But what would happen to the force on that test charge if I doubled it? Okay, well, Coulomb's law tells us that if I double the point charge, then the force on that charge is going to double as well. Okay, however, the electric field strength at that location didn't really change, so we need to figure out some way of negating out the charge on the point charge itself. So the electric field does not depend on the point charge that we're using to measure. It just depends on the charge that's making the field itself. Okay. So what we're going to do is we're going to calculate the electric field E, okay, by taking the force on the test particle and the test charge and dividing by the test charge on itself. So we've got the test charge is little q, and big Q is the charge that's making the electric field. Okay, so E equals F over Q, and note that E and F are vectors. Okay, so let's say we've got a given location where the electric field is 24 newtons per coulomb. Okay, what that means is that there's going to be a force of 24 newtons on that charge per coulomb of charge. Okay, so what would the direction and the magnitude of the force be on a 2 coulomb charge placed at this location? Okay, so again, we're using a test charge, so it's going to be a positive test particle. So that's going to be 48 newtons. Okay, so plugging in the numbers or just kind of reasoning your way through it. The force on that charge is going to be 48 newtons per coulomb, multiplying the 2 times 24, and the direction is going to be towards the negative source charge. Okay. So now we can substitute in Coulomb's law for this force. So E equals F over Q. We just learned that. F, this is Coulomb's law, equals KQQ over R squared. If we put this in, basically what's going to happen is we're going to divide out the test particle, and we're going to get that the electric field at a given location is equal to K times Q, where Q is the source charge. Okay, there's no test particle involved really now, divided by our distance from the source charge squared. Okay, so the strength of an electric field increases with the charge on the object that's creating it. It decreases with the square of the distance from the object creating it, and it doesn't depend on the test charge itself, but other charges can affect the overall field, electric field at a given location if we have more than one source charge. Okay. So some animals have developed the ability to detect electric fields. Sharks are one of those. I forget. Oh, they are the ampullae of Lorenzini. Allow them to detect electric fields created by muscle twitching of the prey. So that's pretty cool. So what is the strength and direction of the electric field? 2.5 times 10 to the negative 9th meters to the right of an electron. So let's work this problem. So the first thing we're going to do is we're going to write our equation. E equals KQ over R squared. Notice the test particle charge is left out. So K is Coulomb's constant, 8.988 times 10 to the 9th. Okay, times Q, which is our source charge, which is an electron, and the charge on an electron is 1.60 times 10 to the minus 19th coulombs. Okay, and our distance from that is 2.5 times 10 to the negative 9th. Don't forget to square that. And we get that we have an electric field of 2.3 times 10 to the 8th newtons per coulomb. Okay, and what would the direction be? I believe we were talking about an electron, so the electric field would be pointing towards the electron. Okay, now electric fields can add or subtract just like forces. So what is shown here is the net electric field, meaning if I were to put a particle at this location right here, it would be getting pushed straight up, okay? Because there would be a diagonal force to the right, and there would be a diagonal force up and to the left. The left and right components of those forces are going to cancel out, okay? And we're going to be left with strictly a vertical component, okay? If I look at right in the middle, okay, there's no electric field. The electric fields completely cancel out. because those forces would cancel out. Okay? So here's two electric fields which are affecting our test charge. What is the direction of each field at its location? Okay, so here's our test particle. Okay, the direction of E1, the electric field from charge 1, is going to be pointed to the left, okay, because the electric field lines point towards the object. The electric field from the object pointed on the right side, Q2, electric field is going to be pointed to the right. Okay, assuming that they're the same magnitude of charge, the field from Q1 is going to be stronger because we're closer to it. Okay. Now, are these field vectors going to add or subtract? They're going to subtract because they're in opposite directions. Okay. And what we'd be left with is our net electric field after we calculated the electric field E1 and calculated the electric field E2. Once we subtract those, we'd be left up with our net electric force vector. Okay. Now, what about the direction of the two electric fields here? Okay, so E1 is going to point in which direction at the test charge location? Okay, that's going to point to the left. Okay, what about E2 at the test charge location? That's also going to point to the left. So those particles are going to, those electric fields are going to add. So if you calculated them, you would just add them up, and that would be your answer. Okay. So what would the direction of the electric field be right here at the this location? Okay, well, we're going to have two attractive fields. Okay, we're going to have one pointed down and to the left, and we're going to have one pointed down and to the right, assuming that they're equal in magnitude. What's going to happen is the left and right components of those vectors are going to cancel, and we're going to simply be left with a down vector, and those down vectors are going to add. Okay. All right. So why is there an electric field outside a conductor? Okay. So this is, I've seen this on the AP test. This is map the electric field outside a charged conductor. So the electric field outside a conductor is just based on the equation that I just gave you, KQQ over R squared. Notice that it's increasing exponentially because of the R squared. Whoops. And then at the location of the surface of the charge, it's KQ again over R squared, where R is the radius of the sphere in this case. Once we go within the sphere, remember there's no electric field within a charged conductor, so the electric field drops down to 0, and then it continues out on the other side. So looking at work and changes of energy by moving through electric fields. So let's say we've got a 2 plus Coulomb charge that's in a uniform electric field of 6 newtons per Coulomb between two charged parallel plates. Okay, if the charge moves 3 meters, how much work was done and by how much energy did it change? Okay, so let's look at the force acting on our charge. So the force on our charge is going to be 12 newtons because we've got an electric field of 6 newtons per Coulomb, and we've got a charge of 2 coulombs. So just multiplying those together, we get 12 newtons. Okay, now remember, work is equal to force times distance. So there's the force which we just calculated, which is that 12 newtons, okay, times the distance, which is 3 meters. And remember, force and direction, motion, have got to be parallel in order for this to do work. So these are parallel. It's moving to the right, and the field lines point to the right, so that's parallel. So our work is going to be 36 joules of work done. And remember, work equals the change in energy. So since there were 36 joules of energy, or 36 joules of work done, we're going to change the energy by 36 joules. Okay. Now what we're going to do is we're going to move our charge perpendicular to the electric field. And the thing here is that it's not going to require any force to move our particle perpendicular to the electric field because there's no force acting on it in that direction. So and if the force that is acting on it is perpendicular to the motion, so there's not going to be any change in potential energy. There's not going to be any work done or anything like that. Okay. Now, if we go at a diagonal, okay, the thing here is that you just need to ignore the, in this case, vertical component, the component that's perpendicular to the electric field, and calculate the component of the direction of the motion that is parallel to the plate. So using the angle of 45 degrees and the distance of 3 meters, and we would just use that component that's parallel. Okay. So substituting in to find another equation, we've got that the electric field equals force over the test charge. So that's the definition of electric field. So in solving that for F, we get F equals QE. Okay, so just multiplying through by Q. Okay, and then if we sub that in for work equals force times distance, okay, we get work equals QED. Okay, and then if we substitute in our work energy theorem, or work equals the change in energy, and we get that the change in potential energy is equal to Q times E times D, where D is the distance that's parallel to the electric field. Okay. And I think that's it for the day. Okay. Well, enjoy your day, and I think it just stopped. No, there we go.